Anyway, let's take a look and find out and learn a little bit about forming rocky asteroids in space, and how do you make the rocks out there.
Sarah did such a great job of introducing us to Arecibo, particularly the most recent work released, including how Arecibo even helped with the DART mission. So Arecibo has actually been one of the most productive telescopes in our observing arsenal, particularly for rocky bodies out in the solar system. It's been responsible for collecting data of over 850 near-Earth asteroids, and it's also allowed us to further resolve other aspects of these bodies like sizes, the shapes, the spins, and even their surfaces. And in fact, Arecibo has also helped scientists confirm that there are moons around these near-Earth asteroids. So we would call those binary and triple asteroid systems in which 2 or 3 asteroids are actually all orbiting one another. So Arecibo has done the lion's share of work in progressing the field of asteroid detection and identification. But if you're as much of a space nerd as I am, you might be asking how these rocks that Arecibo detects even form in space to begin with. So I'll take you all the way back to the beginning of our own solar system, some 4.5 billion years ago. In short, rocks are actually made from stardust. When a star dies, forming either a supernova or a planetary nebula, it ejects plasma and gas of different elements into the universe. So from the death of these stars come the ingredients for the next generation to form. So these protostars form in stellar nursery regions when the gas and dust clouds start to collapse. And as this happens, in order to preserve the angular momentum of that collapse, or the energy of the system, the clouds shrink, they spin faster, and they flatten out into what we call a protoplanetary disk. Then, over the course of the next few million years, these bits of stardust clumps start to slowly cool and stick together. So there's so much material in this protoplanetary disk that collisions are incredibly hard to avoid. And as more and more of these particles collide together, they form larger and larger clumps in the disk. And at this point, these stardust clumps are now called planetesimals. So much like their smaller bits and pieces, these planetesimals float through space, interact with one another, and eventually collide to form larger bodies called protoplanets. So we are well on the way to forming planetary bodies like we see today in our own solar system underneath this model. And thanks to new observations in exosolar systems, we also see what we think are very similar processes happening elsewhere in the galaxy. And so in our solar system, as the planets continued to build up in size, the leftover material was shepherded into different regions of the solar system, such as the asteroid belt, and in the case of comets, the Kuiper belt. So we detect this material today in the form of asteroids and comets, respectively. So a lot of this planet-forming hypothesis might sound like conjecture, but it's actually very well supported through the study of meteorites. So meteorites land on Earth from space, and are rock fragments from some of these leftover asteroid bodies that are still floating around in space. So when a meteorite lands on Earth, it provides researchers with a fantastic opportunity to study this material that escaped planet formation. And so some of these meteorites have collections of minerals in them called chondrules. And these are thought to reflect the earliest composition of the solar system, particularly the sun, and may have formed by a flash heating of stardust grains to approximately 1,000 degrees Kelvin, or about 730 degrees Celsius. If a meteorite has these glassy chondrules, we call them a chondrite. And so chondrules are typically found in non-metallic stony meteorites, and they make up about 80% of all meteorites that fall to the Earth's surface. So we have a ton of opportunities to learn about them. And so these chondrules were molten and cooled before being incorporated into their parent bodies. So they're even older than the asteroids and meteorites that we actually find them in. And so it's through the study of these chondrules and other very old rocky inclusions that we've deduced the age of the solar system to be at least 4.5 billion years old. So you can thank rocks for the age of our solar system. So how does this tell us anything about planet formation in a much broader sense? What about other star systems? Well, studying meteorites allows us to make observations about the mechanisms and the chemical processes of rock formation, which intrinsically allows us to build a history from the ground up of how planets formed. And so throughout the galaxy, we're observing planets around other stars called exoplanets that are in the process of forming today. So coupled with our geochemical measurements of meteorites, these observations allow us to test important ideas and hypotheses about how planet formation works. Much of this knowledge provides the basis for what researchers, like our guest, Dr. Curry, study. So if we can figure out how our solar system started, how rocks first started forming and differentiated into the planets we see today, then we can apply some of this knowledge to exoplanet formation in far off star systems. So thank you so much for coming along on this blast through the past of the solar system to learn about rocks and why they're so important to so many different parts of planetary science and even astrophysics today.